comment that tomorrow, I think, we'll have a Zoom talk, right, from what our other organizer couldn't make it. And then we'll have a discussion and so on for the second part of the morning. The informal discussion thing for the afternoon, it's up to you. It's not going to be any formal event. So the school will basically come to an official close. You're free to assemble and do science. So without further ado, please.
Okay, thank you. So today I'm going to finish up by talking about swimmers in an external flow. We talked about how to calculate the swimming speed for a swimmer in the absence of flow, right? Where the only flow is the flow induced by the swimmer. But of course, that's not the typical situation. At the scale of small microorganisms, they experience shear, either from something happening in the fluid at a larger scale or the other nearby organisms. And then to understand that, I'll talk a little bit more about the interactions between swimmers. And finally, we'll end up kind of circling back to Julia's lectures from the first day, or rather the first week. And I'll talk about the very same instability that she talked about, but more from the point of view of these interacting swimmers and the forces and flows that they exert on each other. So let's start by looking at a squirmer type model, where for now we're going to suppose that the swimmer is spherical, and maybe there's some other stuff in the liquid that's falling or something and setting up a shear flow. And the question is, how does the swimmer move in the shear flow? So as before, we're going to say that the swimmer has some orientation, which, I could, maybe it's Chlamydomonas, it's got its cilia coming out in the front, or we've got this swimming slip velocity that we impose. In the absence of shear, it would just move along this p vector, right? But now this is going to rotate it. So we want to find out what direction this is going to swim in this instant. So v isn't the same swimming velocity we calculated before. We have to add to it the effect of the shear, and the shear is also going to rotate it. So we have to understand how to do that. And because we're dealing with Stokes flow, we can use linearity and just add two problems together. So we've already solved the first problem last time. The first problem is the pure swimming problem with no external flow. So we saw last time how to calculate the swimming velocity. And in this case, the swimmer's stroke is symmetric. It's not pushing more on one side than the other side. So it's not going to rotate. And then we want to add to that the problem of a rigid sphere. So we take away the so-called slip boundary condition here, and we just need to solve the problem of a sphere in this flow. So we'll talk about, it's going to have some velocity, which we'll call VF, F for flow, S for swimmer, and it's going to have some rotation. So in general, we'll just add these together, right? So to get the total velocity that the swimmer is moving at, we just add up the swimming velocity to the velocity from the external flow. And likewise, I always have trouble down here. Likewise, for the angular velocity, in general, there could be some rotation due to the swimming, but we're gonna largely ignore that. VF is the velocity of the flow. So you take this sphere and you put it in this shear flow, and the sphere, because of the no slip boundary conditions, is going to distort the flow a little bit, and it's also going to be advected. So VF is the velocity that the rigid sphere is moved by in this external flow. So to get the total velocity that the swimmer moves at in this external flow, so very far away, we could say that the velocity is V infinity, which is, say, some, shear rate. Whoops, so used to doing it that way, but let's write it this way, I guess. Right, okay? Yep.
Sorry, are these two VS and VS the same or different VS?
Okay, so this VS is what I was saying before, is the velocity. I'll write this out more carefully, but this is the velocity of the material points relative to the center of the swimmer, the material points on the surface. So to get the total velocity of the swimmer, to get the total velocity here, we have to add VS to the swimming velocity.
So it's just a boundary.
Sorry? Just the boundary. This is the velocity relative to this point. That's what we prescribed. That was the, in the last time we had this kind of thing, just the velocity relative to that point. Okay. Okay, so I'm going to review now how to solve this second problem. Again, we have lots of shortcuts when we're talking about spheres in flow. We can use the reciprocal theorem. And so let's call, this is problem A, which we solved last time, and this is problem B. So problem B was solved many years ago. And the answer is given by Faxon's laws. And we're going to look at this in the case where there is no hydrodynamic force acting on this object. And that's why it's moving, right? It's going to be moving advected with the flow. So the question is, how fast does this move and how much does it rotate? So you can take the singular solutions that I wrote down in the notes, and you can just solve this problem directly, or you can use the reciprocal theorem. So it comes from and of course, you need you need two problems when you apply the reciprocal problem or theorem. One of the problems is the Stokes problem. Again, we use this fact that the traction, the stress dotted into the normal on the surface is in a constant direction, and it's constant in the in the Stokes drag problem. The other problem is basically looking at the disturbance flow, looking at the velocity that you're trying to find and subtracting off this V infinity. So you can look at the references, or you can try to work that out yourself. I won't go through it. I'll just tell you what the answer is. So again, this is for the case where there's no hydrodynamic force and there's no hydrodynamic torque. So in this case, and again, this is for spheres. And we'll say that V, as you get very far from the sphere, I'll call that V infinity. But this is more, this is more general than this linear shear flow. It's just any flow. This could be anything. So the result is that the velocity that the sphere moves at is the velocity. I'll use 0 for the center of the sphere. So you take this flow, the undisturbed flow, and you look at what its value would be at the center sphere if the sphere weren't there. And it just gets moved along. And then there's a correction. There's a finite size correction, which has a very simple form. And it only involves, it only depends on the radius of the sphere. And this is sort of like the curvature of the streamlines, two derivatives, right? So this term, take the sphere away, the undisturbed flow. Sorry, I missed that last sentence. It's
You're saying there's an R going to infinity here, but I don't get it. It's not.
Well, this is the boundary condition. So this is the flow that we're trying to find. And I'm saying that, well, you actually don't have to find that flow. You can use this Faxon law to get the velocity in terms of what it would be, what you said, the undisturbed flow. Yeah. Could be anything. Anything. Well, you take whatever your flow is, some crazy flow, and you stick a sphere into it. And that sphere, because of the no-slip boundary conditions, is going to change the flow a little bit. But the point where you put the sphere, that this velocity right here in the undisturbed flow is v infinity of 0. So the infinity here means that it's the velocity. It doesn't just mean it's the velocity far away. This whole. What did I? Well, okay. Yeah, there's two. Okay, here this flow is v infinity of x, and then the actual flow with the sphere in it is going to look a little different. Far away, it's going to be the same as v infinity, but nearby here, it's going to do something else, right? So this, far away out here, right? Out here, v of x is equal to v infinity out here, right? Well, it's terrible, right? Out here, right? But in here, it's different, right? Because of the no-slip boundary condition. So v infinity is defined everywhere. So, we're mostly going to be thinking about cases like this, where we've got a shear flow, and it's, because at the scale of a bacterium, we don't have to worry about curvature. Yeah. Oh, I'm sorry. Okay, thank you. I missed that. Thank you. That's what was confusing. Thank you. Okay. Okay. All right. So that's what happens to the sphere, to its linear velocity, and mostly we're going to ignore this term because it's a finite size effect. It's if there's some scale to the flow over which this varies, then the correction is small. And of course, it's equal to 0 for any linear flow, right? There's no correction for a linear flow. So the simple shear flow I drew over there, or an extensional flow. So the second length scale L is just the scale of change in this background flow, in the undisturbed flow. So if I look at this over here, I take two derivatives, I'm going to get something like a squared over L squared for this term. So for swimming microorganisms, this is typically going to be small. Okay. And then you can do the same thing for the rotation speed, the angular velocity. And what we find is that this, well, kind of the simplest thing you could imagine. Again, you look at this background flow, and you evaluate it at the point where you put the sphere, and the rotation is the vorticity. The sphere just rotates at the rate that the flow at that point rotates. So for a sphere, the sphere rotates steadily for if you have a constant vorticity. Like in that simple shear flow. There's no a squared correction.
Slight change in vorticity.
Yeah, no, there's no a squared correction. No, this is it's all exact because you basically have an expansion, and because the vorticity is harmonic and the the velocity is biharmonic, all those higher order terms drop out. That's right. Okay, so now what we can do is we can use these laws to write down the equations for the trajectories and figure out what the orientation of the swimmer is. So let's say we have some axis here, and I'll use capital X for the position of the swimmer. And P is the, its orientation. And we just add, we use superposition. We say that X dot is going to be the velocity of the swimmer plus what we get from Faxon's law. So now we have to evaluate it at the position of the swimmer. And, if we want to be really accurate, we have to include this other term. And likewise, well, we won't worry about the swimmer rotating on its own. We just have the vorticity here. Yeah, so P is a unit vector, and we just evaluate this at the point of the swimmer. So there's simple results that you can get for linear flows. You can solve this problem exactly for certain flows. So for simple shear, see if I can draw this. So now I'll say that the background flow is gamma dot times y in the x hat direction. So that looks like this. And the swimmer makes a kind of a cycloidal path. And you can see that if the swimmer is going this way, it's going to tend to rotate because of the shear, and it's just going to keep rotating. It's going to rotate and go all the way around, and you can write this out and solve it. I'm not going to talk about noise and Brownian motion at all in these lectures, but of course noise has to be taken into account, and noise will dampen the oscillations. And there have been many papers that look at these things experimentally and theoretically. Another example is Psi flow, which is a little more interesting. What happens in Psi flow? So here it's different depending on whether you're swimming upstream or downstream. So maybe I'll just draw two pictures. So for upstream swimming, so we're going in this direction. Again, it looks kind of like the cycloid that I drew. But the interesting thing is that the P vector, you can kind of work this out by looking at which direction the shear is going to rotate. So here in the bottom, this is going to be rotating up, so it's going to go up. And then up the top is going to rotate the other way. So we call this upstream swinging. So P rotates back and forth between two extremes. So P is just going back and forth like that. Whereas in the downstream case, don't quite get these loops. I mean, it's going to depend on where you start and where, we're not worrying about the walls or anything like that. And now, if you look at the rotation, it turns out that this rotates all the way around. So people call this downstream tumbling. And again, there's, Brownian motion can make you go from switch direction, like people have seen E. coli go from one of these trajectories to the other. I think I saw Norris here earlier. So she tracked bacteria just a few years ago and saw these trajectories in real life. So I encourage you to look at those papers, or that paper. I have referenced it in the notes. But applying this to bacteria kind of brings up a natural question. I was talking over here about spheres, and spheres have a lot of symmetry. And the question Peter raised about, well, is it really just going to rotate by the vorticity? That doesn't happen for a rod, right? Bacteria are more like rods. So really what we'd like to do is look at the same problem for a swimmer that's more like a rod. That would be more realistic and is worth looking at. So that's the next thing I want to talk about. And the point is that the sphere has a lot of symmetry. That's why it's rotating at this uniform rate. But rods have a non-uniform rotation rate. So again, if we have a shear flow here, you can see that if the rod is, I think I said last time, if the rod is perpendicular, this is going to rotate fast. So let's just call this omega from the flow is fast, relative to what it does when it's aligned with the shear, or rather aligned with the streamlines. There's still going to be some rotation, right? The rod has some thickness. So there's a small difference in the velocity on the top compared to the bottom. So there's a little bit of torque, just not as much as we have over here. So omega is going to be slow. So this is something that you can work out exactly in the case of a very slender rod using the resistive force theory that I wrote down for you last time. So that's a good exercise. I won't do it here, but I'll just give you the results. The question is, how fast does the rod rotate? So use resistive force theory. So you take a rod and a flow. So let's say the flow is a linear flow. So A is a constant for us, because again, we're thinking about the small scale where the flow is going to look linear. And you have your rod here. It's got some orientation. And what you have to do is you have to calculate the total force. So remember, we said that the force per unit area by resistive force theory is a perpendicular coefficient, drag coefficient, times the velocity perpendicular to the rod, plus a parallel component. And the key thing, and for the formula that I'm going to write, I'm going to say that this perpendicular drag is exactly twice. It's not the formulas I wrote down, it's not exactly 2, but many people just, for what we're doing here, we'll say that it's equal to 2. So the result is that the total, and you say that the total force, the integral of f, let's say there's some arc length here, the integral of s ds is equal to 0, and the integral of r cross f ds is equal to 0. You say 0 torque and 0 zero force. And what you find is one piece that looks just like what we wrote down for the spheres. We've got that there's a component of the rotation, which is exactly the vorticity. Omega is, oh, so what did I do here? I think I wrote this wrong in my notes, but that's okay. No, that's right, 1/2. Yep, and then there's another piece. And this other piece, we've got this projection operator, and it involves the strain rate. So sorry, what did I, yeah, I thought I must have written this wrong here. Thank you. Thank you. Yeah, I wrote it wrong in my notes last night. So this is what it should be. Yeah, it was because for the sphere, it was 1/2 curl, 1/2 curl of V. Thank you. And E here is the strain rate. So E is just the strain that we get from our linear flow. So we need to have this here, it just pops out, but P is a unit vector. So if I dot the left-hand side, the only way that P can change it is its direction because it's unit. So this is, of course, is perpendicular P, and this I also have to take care of that as well there. This is the time-dependent piece, right? So if I look at a flow, look at shear flow, for example. So I can write it as, I think I wrote this down last time as well. I can write it as this kind of sum of the extensional and rotational components. And you can see certainly, over here, I don't know what happened to the yardstick, but here's the uniform piece. And here you can see that the rod's going to want to tend to align along the principal axes here of the strain. So that's the non-uniform component of the rotation. And that's for very thin rods using resistive force theory. Thank you. Okay, so here's my big moment. Here we're just doing uniform rotation. Here, it's going to tend to want to align. So thank you. There's a similar result that actually goes back 100 years, right? This is the 100th year anniversary of Jeffrey's paper. This motion, I guess I can do it again, right? This motion of fast and slow and fast. And it's even more interesting when it can go out of the plane. Those are called Jeffery orbits. So Jeffrey solved the Stokes equations exactly in 1922 to find what the evolution of P would be for an ellipsoid. So we'll just draw a prolate ellipsoid here. And again, we have a semi-major axis A and a semi-minor axis B. So the result, I'll just write it in components this time. And here I'll write it slightly differently just because this is another way people write it using this, the antisymmetric part of the strain. So, Suzanne mentioned that, I always have to write these things out, the kind of confusion, the different conventions for the order of the indices. That's the convention I'm using here. Just kind of have to check it every time to make sure it's doing the right thing. So what is B? B is a factor that depends on the shape. So B is r squared minus 1, r squared plus 1, where r is the ratio of these axes of the ellipsoid. So when B is equal to A, r is equal to 1, capital B is equal to 0, and we just get back the uniform rotation of a sphere, which is what we would have to get. And when we have something which is long and slender, r is very, very large, B is equal to 1, and we get back the resistive force theory. Sorry, I switched it in my notes. R is A over B. Thank you. Thank you. So R is getting big if it's long and thin. Yeah, I have it exactly opposite here. Okay, so now maybe I'll get you to lunch a little bit earlier today. What I want to do is put all this together and study how a collection of cells, swimming cells, are going to interact. And in particular, we want to go after, we'll write down the general equations, we'll take a certain limit where it's easy to look at mathematically, but these equations can be used in many different situations. The situation that I'll look at is if you have a uniform concentration of swimmers with isotropic orientation, their rods can all be pointing in all different directions, and ask, is that state stable? And we've seen already that the answer to that question depends on whether or not the swimmers are pushers or pullers. And then also as a bonus, what we'll see is that the answer that we get actually doesn't depend on the swimming velocity. So it will also apply to the case of a active matter with nematic symmetry. So that's where we're headed here. Oh, by the way, I guess I have one more. I say it here in the notes that there are lots of applications of this idea to the case of swimmers near a wall, right? So swimmers near a wall tend to orient depending on whether they're pushers or pullers. I'm not going to work out all those things. You can look at our review article or Eric Lauga's book. Also, a very interesting case is swimmers that are subject to an external torque. This active matter field goes back very long. John Kessler is one of the early workers in it who looked at the so-called gyrotaxis of these swimming algae, which are bottom heavy. So they experience a kind of torque and they tend to align. And there's a very interesting story there. So I'll just, if you're interested in active matter, I suggest you look at these papers because they're interesting and they're just early examples. Why do these algae swim up against gravity? Okay, so let's suppose, so now, yes. I didn't hear the whole question. These Jeffery orbits are for any, it's for any linear flow. So it's really basically pure flow. That's what he was studying. Yep. That I don't know. I suspect, well, it's certainly solvable if there's any large ratio of any of those. He did I don't know. I mean, I think it's this is kind. I've never actually gone through it. He does it in bipolar coordinates. It's sort of complicated. Something that maybe in 1922 people at the equivalent of this summer school would just be able to knock out, but it's a little bit complicated. It doesn't have to be very thin, very extreme. Maybe, I don't know, 8 times A is 8 times B before the resistive force theory is very accurate. Which just fits with the idea that the shape is not all that important at low Reynolds numbers. Certainly matters, but yeah. Okay, so let's look at the case of many swimmers. And again, we're going to really rely on an assumption of diluteness. It's going to help us write down things more or less, well, in an easy way. So we have some large volume where we've got some cells. You know, this picture I'm drawing looks nothing, this is the limit we're going to take. It looks nothing like the experiments that people apply these equations to, but that's okay. This is just going to be a kind of a simple shortcut to writing down the equation. So A, as before, is this kind of characteristic size of the swimmers. And let's say that their typical separation is L. So A is much, much smaller than L. And we're going to say that each swimmer is going to feel the flow induced by the other swimmers, but because they're far apart, we're just going to take the leading order bit. So they're going to feel the stresslets. So we're going to think of this as a bunch of stresslets. So what do the stresslets do? Set up a flow that's going to tend to orient the cells, which we just saw here, how to handle that. And because they're far apart, whatever that, we don't have to worry about the near field of these flows. We can use the far field and basically treat the flow that this cell sees from this well. We can treat that flow as linear, and then we can use that formula. And finally, what is the effect of the swimmers on the flow? The swimmers are going to make some overall flow. We know how to do that because we saw last time, I went through it very quickly, but in response to the questions, I kind of wrote out you can derive it. I wrote out all the steps in the notes, which I'll post later today. We know that the mean, if I think of this as a continuum, the mean stress is given by the stresslets. So I have to just add up all those stresslets. So that will be the active force. So let's put all that together. We're going to use the distribution function for the swimmers. So in the kind of usual way. So psi is the number of swimmers in a volume, a little volume d3x about x, and a solid angle d omega about p hat. So this looks like what Ellen wrote down, but p is not momentum, right? P is the orientation. We only have those things. So of course the density, I'm going to use n for number density. So n of x and t, we have to integrate psi over the orientation. And we can write down an equation for psi. So this is one of the main references in the classic calculation I'm going to review today is Santillan and Shelley. I forget when that was. It's in the notes. 2008. So they're using the same formalism, which is familiar to people who work in polymer physics, where you write down an equation for how psi evolves in time, which I'll do over here. So it's like a probability, so it has to be conserved. So the governing equation for psi so I have a current for, I'll explain what these currents are in a moment, but there's one corresponding to x and one corresponding to p. And p is a unit vector, right? So really I should write p theta and p phi, right? The angular coordinates. So this, what do I mean by this? I don't want to write all that out. So what I mean by that symbol here, it has to be something that when I dot p into it, I get 0. So I'm going to treat p as if it were just a 3-dimensional vector without any constraints and put that projector out in front of it. That's what I mean by this symbol. That it's just a derivative on the surface, the tangential derivative of the surface of the sphere. So how can psi change? Psi can change because particles can move. Let's first just talk about how particles can move in space. So particles can move in space because they're swimming. So there's a contribution to the flux, which is just the velocity of swimming times the concentration. Particles can also move, or psi can change because particles are moved because of the flow. So whatever the flow is, we're going to have to solve for the flow. So we've got that flux. And then particles, or psi can change because particles might just be diffusing around randomly. So we've got, the Fick's law contribution. Likewise, for the flux in the angular coordinates, we can say the same kind of thing. Why would this concentration, or why would this distribution change? It changes because they're particles whose p's are changing. So why does p change? P could change because, well, I said we were going to ignore this. So there could be some, just the fact that the swimmers, due to their intrinsic swimming, they're flapping more on one side than the other, they could reorient. But I'm going to ignore that. There's there's this whole, let's just say omega cross p plus, and let's say their ellipse, we'll put in some fudge factor b. So psi can change because the particles are rotated by the flow, right? That's one way it can change. And then, of course, there can be rotational diffusion. Okay, so that's our equation for psi. Yes. Yeah, thermal motion, or maybe some kind of intrinsic. I'm immediately going to throw them away, but they are there. They were there in Santillan and Shelley's calculation. So due to Brownian motion, E. coli on its runs and tumbles when it's swimming straight, eventually it gets knocked off course a little bit because of Brownian motion. So it's definitely there. There could also be some kind of intrinsic randomness to the swimming that we could model in this way. The rest of the terms are from the calculations we just did, that there's why does psi change? Psi changes because particles move. They can move because of intrinsic swimming, because they're advected by the flow, and then Brownian motion, of course. There's another question. Okay, thank you. Or you're welcome. Okay, so so we have an equation for psi, and now we want to write down an equation for the velocity. So what we're going to do is say that the swimmers, let's say it this way, each swimmer sees the other swimmer's stresslets. So and they're in the far field because it's dilute. So we say that the velocity that the other swimmers see is this stresslet thing that I wrote down last time. And the form that we'll use, again, I wrote this kind of more generally last time. But if you look, remember I had let me write it first. I had I had forces, right? I had a force dipole, and there was one vector E along the force, and then D was the vector between the two forces. For an axisymmetric swimmer, we're going to consider axisymmetric swimmers. Everything is along P. That's the only vector we have in this case. So E and D are equal to P, and you kind of look at what I had before. This is what you get. It's the only thing, that's what you can write this down immediately. I guess the only thing is to get the sign of P. So just working out what we had before. Positive P corresponds to pullers, extensile particles, negative. I was writing this down. I knew I was writing this wrong. Extensile particles are pushers. Contractile particles are pullers. So pushers have positive P in this convention. Okay, so now we can use Batchelor's formula to calculate the stress induced by the swimmers. So Batchelor says that from the swimmers, that's what the S is for. Deviatoric means there's no trace. This is where we kind of ended last time. So in terms of psi, we can write this down in terms of psi. We want to integrate with our distribution function against S. And there it is. So we're going to write it this way. I'm going to pull off a factor of -1 and write this as psi. Just write it in the other order, PP minus a third times the identity, integrated over all the angles. Right, so that's with the minus sign. Get all the factors. That's our pneumatic order parameter tensor, right? Most people write it with the vectors first rather than second, so that's why there's this minus sign here. So this is Julia's term that she used in the equations. So in her active, one of the active terms, the main active term, the one that does everything. So now we put that into the Stokes equations. We say that we've got Stokes, or as Suzanne said, the extended Stokes equations. You remember this is the divergence of the pressure. So we're going to have minus, I could write it this way. So P is a constant. It's very interesting to look at what happens to concentration in active swimmers or active matter, but I'm going to ignore that. We're going to take N to be uniform. This is, just for this very specialized calculation that I'm going to do. This is not generally true, but just for today, we're going to take N to be uniform. So, and this is a very common thing that people do. So they take that density out or that concentration out, and there's your minimal model or at least the force balance minimal model for active matter. Okay, so perfect. Are there any questions so far? Yep. Repeat the argument for what? Oh, so this term is the it's the rotation you would get because your swimmer is somehow asymmetric. So maybe you're pushing more on one side than the other side. In other words, if there were no external flow and there's just a single swimmer, this is a swimmer that would swim around in a circle, right? So I'm saying we'll just ignore that. Going back to the first lecture, when I mentioned the Purcell swimmer, that's an example of a swimmer that it's going to rotate as it's swimming because of its asymmetry. So in general, it's there, but we're going to assume that our swimmers are more symmetric. Okay, so let's do some linear stability analysis. Now we've coarse-grained the system. We're talking about the mean stress. V is the velocity at every point. So even though I said it's dilute, we're now working with a continuum model where we imagine that everything, like the concentration is uniform. So what we're going to do is study the stability of the isotropic state with V equals 0. So what does that mean for V equals 0 when the swimmers are all swimming around? It just means that the velocity at any volume averages to 0. You have a question, Leo? Yes. You could consider a pneumatic fluid.
In other words, this S is not the pneumatic order.
So what people do is it turns out that it would be the same if you were to write down a model of an active pneumatic. This would exactly be that S, or this S would be the usual Q.
What is it in the isotropic fluid it represents?
Well,
Directional axis picked out by the stroke?
by the swimmers, that's right. So they could all be aligned, for example.
Right, so isotropic just described by P at average be 0.
The average of this would be 0. Yeah.
Right, but
Yeah, so this is describing a solution. So this here today, I'm talking about the order of the swimmers. That's what Q corresponds to.
that they're all swimming on the same axis.
Okay, so I haven't averaged this yet. This is like the microscopic, right? It's the Q over there. If I,
Over there,
yeah, exactly. So I have to look at the eigenvalue of that to get what you're talking about. But the equations are the same. You know, Julia, she talked about these models for these extensile microtubules, and then you really just have a pneumatic, and you know it's dense everywhere. And then you would just start by writing. Well, there's a salt. You know, in reality, there's a solvent, but we think of it as like a lyotropic pneumatic, something like that. Yeah. So then you would write down this, and then there'd be other terms, you know, coming from backflow and things like that I haven't written down that you'd have in a liquid crystal. But you would have the same term in a active pneumatic.
I guess I'm wondering, suppose on average that Q is 0.
Yep.
Pneumatic order from the swimmer.
Yep.
What is the next order active term you would add to the Stokes?
There isn't one at this level. What we're going to see is that these other effects, this orientation effect can, you know, when there's a little bit of shear because of the swimming motion, can induce some pneumatic order locally. So even if that's what people call the active gels, right? That it's isotropic, except for the fact that there's some shear which would locally order it. That's exactly what we're going after. Okay. All right, let me recharge my chalk here. Okay, so the isotropic state, we're going to say that isotropic state would be that, the p's can point anywhere on the sphere with total solid angle of 4 pi. There's a uniform concentration, which we're not going to allow that to vary, and then we're going to add to that some perturbation. And the perturbation is going to be of the form, just the simplest thing we can imagine. Just a plane wave with some exponential growth, because we're doing linear stability. And we want to see, is sigma positive or negative or zero? And the velocity, there's no velocity to start. So the velocity is going to be first order. There's no velocity in the base state. Okay, so now we just have to linearize that equation, the force balance equation, and we have to linearize what happened to it? We have to linearize that equation up top. So maybe I'll leave that there. I'll leave that bit there. Okay, so from the first term, well, first of all, let's write it like that. So, x and p hat are coordinates, so I can take the p hat outside of that x gradient. So that's the swimming velocity of the individual cells, v. And I'm not going to get anything from this term, right? So I'm linearizing, right? So only one of these can be first order. So if v is first order, if I put v1 here, I have to put psi 0 here. And that means I'm going to hit v1 with the gradient, and the perturbation to the flow must be incompressible. So that's going to get wiped out. Likewise, if I put psi 1 here, I have to put v0 here, but v0 is 0. So I don't get anything from this term. I should include this. Santillan and Shelley included this, but now I'm going to throw these terms away. I'm going to throw the diffusive terms away. We're going to look at the long wavelength limit. These terms are important. If we're not in the long wavelength limit, but they're, for k equals 0, they're not important. We can get what we need by disregarding them. Then finally, there's that last term. And again, we're going to throw away the rotational diffusion. And this is all that we have left. So what is this? This is saying that, psi is going to change because particles are being rotated by the flow. And we're thinking of the flow in the far field of all the other swimmers as a linear flow. So this first bit is not going to make any contribution because you can check that. The particles that leave the little volume are going to enter the little volume. This is corresponding to the uniform rate of rotation that I drew over there with the circles. That's, you can, because of the way that the p's are perpendicular to the projection, you can check that. That doesn't enter. The only thing that enters is this term. So I have to take the divergence of that. And you can see there are 3 p's here, and you can be more careful than I'm being right now. And it turns out there's a factor of 3 that enters here. So yeah, thank you. I erased it. So used to working on my iPad, I feel like I should grab this and just slide it over. It's very strange. Yeah. So that's this term is coming from that divergence over there. And it's really only this that survives. There's 3 p's, there's a factor of 3. And again, when you work through it, it's only because there's no strain to 0th order. So it's only the strain that enters to first order. Okay. And then we have to linearize this. So we'll have, I'm going to use capital P for pressure. It's not that important, but you know, we're going to eliminate it in the usual way. And then we have to take this, although I can't even see it from here. We have to take the, oh no, here it is. This expression for Q and write that out. So we have the divergence, and this is the X divergence because, you know, and I'm writing these P's with a prime just to emphasize that psi is a function of X and P, but here we're integrating over these P's we're integrating over, right? We're integrating over their angles. I dropped, you know, there could be a psi 1 times this identity. There's an isotropic piece that I haven't written here. We could just absorb that into the pressure. So thank you. Psi 1. Yep. Okay, so we've actually seen how to solve these equations several times. You know, we know what the, you know, we're going to work in, we have plane waves, right? So we're going to write this as proportional to e to the I kx and all that. We know that the Green's function for Stokes equation is the Stokes slit. We saw that written several times in momentum space instead of the identity plus x hat or r hat, we get the identity minus k hat. I think we saw that yesterday or maybe the day before. In Suzanne's lectures, we can use incompressibility to eliminate the pressure, and we can do all this. I'm just going to write down the answer in a way that maybe you can, maybe an answer along the way, right? An intermediate step. So you can do a little bit of calculation, eliminate. So it's basically just what I said. Here's that familiar bit coming from the Stokes slit. And then there's the driving force, or the Fourier transform of the driving force. I don't know. You have to be a little bit careful about what gets dotted with what. I'll let you work that out. So that's V1, the amplitude of V1. And then you can take that and put that over here. You can see you're going to get a sigma plus Vp dot k. And then you're going to have to use that V1 and you have to put it in here. So then there's, you know, a little more algebra, but I'll just write it out here. And there's a reason I'm writing all this out. Okay. We know that the velocity perturbation V1 is transverse, right? It's got to be perpendicular to K. And we see that right here. And that's basically what this is. So V1 is in the K perp direction. So we can use that to solve for these amplitudes, because we can see that psi1 tilde is going to be proportional to the dot product of p and k hat, right? We're trying to see how does psi1 depend on p. So it's proportional to p dot k hat, and it's proportional to p dot k perp, because it's, psi is going to come from the velocity, and the velocity itself is transverse. So we can say in the long wavelength limit, we can see right there, we can see how psi depends on, see what its angular dependence is. So saying it a little more precisely, psi1 has this angular dependence that I just mentioned, this explicit angular dependence. And then it's got to be some, function of k and p, and this has got to be a scalar. And the point is that as we're going to look at the long wavelength limit, as k goes to 0, we can get out the dependence, the angular dependence. Well, let me just say it this way. And there's higher order terms. I'm being a little hand waving at this point, but this is the essence. You can, from this equation, you can take the long wavelength limit, and you're left with the angular dependence of the leading terms. Gamma here is a constant. So now stop and kind of relax and say what. I'll come to that. It's going to drop out. I may have missed a factor of k somewhere. I seem to have missed a factor of k somewhere. So I'm going to leave that as an exercise. Setting that aside, the end result, you can put this in and solve and track that down. The end result is that the growth rate looks like this. So we can, this is the most important thing of this past 8 minutes of talking. First of all, if you have spheres, it's neutral, right? There's no growth. So the case of spherical swimmers is neutrally stable. Yeah.
I'm expecting spherical harmonics to come here. If the interval psi1, that term, that Q or whatever has some interesting angular behavior. I'm just curious. You made some.
I've
Missing something, or sort of deal with it?
not really. Those are all, they're going to be involving the higher order k's. It turns out this ends up just being sine 2 theta. To leading order, it's really just this p dot k hat and p dot k perp. What you're talking about comes in at higher k's, coefficients at higher k's.
So this is the gross rate of velocity of the swim.
Yeah, I'm going to draw a picture in a moment, but it's the growth rate. So V1, I erased it. It's a shear, right? So it's a growth rate it's a spontaneous shear, and also a spontaneous alignment. The fact that Q is going to. I'll draw a picture in a moment.
This is, I missed a little bit. You assume there's exponential growth.
I'm just linearizing the equations about the isotropic uniform state with no motion.
Right. I'm just wondering, well, at some point it has to saturate.
Sure.
This is just initial growth.
This is just the initial growth, just linear stability analysis. Doesn't tell you where it's going to go. I mean, that's really the focus of Julia's lectures. Where does this end up? What is the? Yep, exactly. This is just the very simple instability. Okay, so spherical swimmers are neutral, are neutrally stable. Pullers are stable, and pushers are unstable. So pusher, I think of these as extensile. This is contractile. And also, we see here that the growth rate is independent of the swimming speed. So that's why this kind of analysis, or at least this result, still applies to an active pneumatic. Or really, we should say an active gel, in the sense that this is a pneumatic that's in its isotropic phase in the absence of the activity. That too is, if it's extensile, so a slightly different take than Suzanne. I think of these microtubules as extensile. Of course, they're, the Dojic system, there's going to be, they're sort of both, right? You have these microtubule bundles where there are motors in between that are sliding the filaments back and forth. So, when the filaments first come on, there's a contractile nature to it. And then after a little while, before it falls off, it's going to be extensile. So it's partially contractile, it's partially extensile. Most of the time, it's going to be doing this. So we talk about it as if it were extensile, but it's somewhere, it's more extensile than contractile is what I would say. Although there are many new results in the system where you add, say, a background pneumatic, and you can get this system to actually contract. So there's more to it than my simple picture here. Anyhow, let me get back to the questions that both Peter and Leo raised, and just try to draw a picture. Let me draw it over here. Just how to visualize this instability. Why does it happen? So here's P, and we can take the z-axis of P to align with K, the P space, and we can just take V1, maybe along the X direction of P. So this fact that psi1, this distribution function, is proportional to P1 or P dot K perp, means it goes like sine of 2 theta. So there's some uniform initial distribution of the P's, and then the perturbation looks something like this, right? So that's why I drove the P. The P's are, the perturbation is at this angle. So if I look at velocity, right? So we have this spontaneous shear, which is set up by these, this is the perturbation. We have this shear. And we see, did I write it over here? Well, there it is. You see there's a factor of I relative between V1 and psi. They're 90 degrees out of phase. So what does that mean? It means that in the places where you have the least shear, we have the most velocity, the amplitude is the greatest, you're not going to have any alignment. Right? You need shear to, in the Jeffrey's orbit, the rods are rotating around continuously, but because they're rotating at a different rate at different times, they're going to spend more time aligned at 45 degrees to the flow than they are, aligned with the flow, right? So they're continually changing. If there's no shear, you wouldn't get any alignment. Here you would get the most alignment. And for the case of a pusher, you can see that the flow induced by the the extensile particle is going to add to the shear flow, and it's going to tend to rotate more. So this is why there's going to be instability. So pushers enhance the shear, and that's why they're unstable. Whereas if I look at a puller, I'll draw the puller down here. So again, the puller is going to align. If you have a bunch of pullers, they're not going to be aligned very much here because there's no shear. They're going to be aligned mostly here in regions of high shear. And the pullers are pulling towards themselves. So they're fighting against the shear. So pullers dampen the shear. And the spheres, why don't the spheres do anything? Well, the spheres don't align, right? So they're pointing every which way in the flow, and there's no feedback at all, and therefore no driving of the system to be unstable. Okay, so I'm going to stop here. You know, what I tried to do today this week is just to go over the physical framework for studying the hydrodynamics of swimmers using, you know, very simple ideas, not shying away from the fact that Stokes flow is linear and just using calculate how fast an organism moves, but how it interacts and how it moves in flow. And you know, my attitude is that a lot of these problems, again, as we've seen all month, I guess here, at least, you know, for the talks about this kind of thing, they're all nonlinear, right? Because of the interactions. But the kind of stuff I talked about this week is very helpful before, or maybe while you're doing your numerical simulation to kind of, you know, test some simple ideas to see if is this a good direction to go in. And finally, although there, you know, in the past 10 or 15 years, there's been a lot of work where people have worked out all of these sort of simple calculations that you can do analytically. I think there's still a lot of room in sort of more applied problems, looking at problems in marine biology or reproduction or infectious diseases. So, so thank you again for the chance to come here, and I'll stop here. Down here, I just drew it down here. The shear is oscillating in space. So down here, it's tending to rotate it this way. Did I draw it wrong? Yeah, oh, I see what you're saying. The puller is tending to make a shear that's opposite this external shear. So it's tending to reduce it. Another way to say it is that, you know, if you took this swimmer and put it in between two plates like this, and it's a puller, it's fighting against the motion you're making, and it's making the effective shear viscosity higher. Whereas over here, it would make the effective shear viscosity lower. And that's another way to think about this instability. Effective shear viscosity goes to 0 for these pushers.
Sorry, it's kind of an embarrassing question because we've been talking about pushers and pullers, but I still don't understand the difference in the sense of, you know, this thing is a cyclical, right?
Yep.
It's not like you push one half a cycle, the next cycle, half a cycle, you're going to pull to reset. So is it just how asymmetric it is in the beginning?
Well, no, I would say that no, these are you can be cyclic without going from pusher to puller to pusher to puller. So for example, a bacterium like E. coli is a pusher, and the cyclical part is just the revolution of the helix. So it's always pushing, the tail's always pushing this way, and the head's always pushing that way. So for its whole cycle.
But like when you're doing this, let's say you're doing this stroke, you're swimming,
Yeah.
you're pulling in, and then you.
There's some, so Chionomonas is a good.
Gathering it, but when you're maybe pushing forward, when you're effectively for that half a cycle, you're a pusher, you somehow do it in such a way that you have less effective approach?
Yeah, I think that's right, that the recovery stroke is not, it's not symmetric. The power stroke is not symmetric with the recovery stroke. That's right. Yep. I didn't,
Sort of like my sparkle.
I didn't think when we do the linear stability analysis, why don't we assume a waving? Oh, well, so here psi, our variables, our dependent variables here are the velocity and the distribution function. So if this is a slightly different point of view where I'm working in terms of psi and the velocity. I could have done this the way that you suggest, which is the way that Julia Yeomans wrote down her equations. You just write down equations for Q and the velocity and assume a waving Q or waving P if it's polar, and you get the same result. This is just a complementary way of doing it.
You could put any dependent issue side where you want it.
Yeah.
Get integrated out, discover that this fits the box.
Yeah. I mean, we put in, that's right.
We didn't limit.
We didn't limit it. Right.